Okay, so here let's come down, get a little more space here, and one of them is accuracy and the other is precision. So accuracy versus precision, and the book has this nice little diagram. I'm going to duplicate it here because it's sort of a nice way of representing the difference between accuracy and precision. And this example comes from markmanship. So if we put precision on this axis and accuracy on this axis, and then let's make a little target here, and we'll have 4 different targets. 1, 2, 3, 4. Okay, and then we're going to start shooting holes in here. So low accuracy, low precision. Okay, so that's going to be something low accuracy, low precision. It's going to be highly spread out of the marked bullet holes over here. Okay, and as we increase our precision, we may still be off the mark, but these shots are going to be grouped much more tightly together. You see, we've tightened our grouping here. And then accuracy, well, this is may still be accurate here if we maybe spread them out like this. We aren't really that close to the target, but if you take the average overall, you actually have fairly close to the center, where if you get both accurate and precise, well, then we're hitting right on the mark, and we have a fairly tight grouping. So that is the accuracy, of course, versus the precision. Okay, now we're ready to firmly define an established formal definition of error. And the first thing that we need to do is to define well the definition of a true error. Okay, so true error is the true value. Well, maybe the first thing we should do is say the true value equals the approximation plus error. And so this is the notion that we have of error. Then we can just rearrange these equations, and we have the error is equal to, or the true error is equal to the true value minus the approximation. And that's how we were going to define it. And so given that, then we can define our true fractional relative error. So in order to do that, we just say that we're going to call that an epsilon of t. Okay, epsilon of t. Epsilon of t is the percent relative error that is just equal to the true errors as defined divided by the true value, and to make this percent relative error, which is multiply it by 100, and that is the percent true percent relative error. Okay, now we can do the exact same thing for approximate error. So we say epsilon of a. So approximate percent, well, what do we call this is percent approximate error. Okay, so this is our approximate error. our percent approximate error is going to be the approximation, or the approximate error divided by the approximation. Okay, so we could call this the approximate value times 100. Okay, that's the percent approximate error. And then of course, I skip one step. How do we come up with our approximate error? Well, it depends on what method we use, but often we use an iterative method. And if we use an iterative method, then what we can do is we can say that the approximate error is equal to the current approximation minus the previous approximation. And that gives us some idea of what our approximation error is, and we have to do this because we don't always know that the true value is. In fact, we seldom know that the true value is. And let me just note, as we go through this, when we're talking about true value, we are only talking about the true value according to our mathematical expression. This true value according to the mathematical expression may be completely different from reality, because here only talking about we are only talking about numerical error. Okay, so this is only for numerical error. Okay, so first we can look at the different sources of error. As we talked about before, we come up with a mathematical model that we want to use to we have this math problem that we want to solve, and then apply the solution back to the real world problem. And in that whole process, we have errors that accumulate from a lot of different sources. And so I just want to outline a little bit what the different sources of error that we have here and where they come from. So here we go, sources of error. Okay, so we have what I'm going to call modeling error. Okay, modeling error. And modeling error comes in different types. Okay, so we have blunders, which are just human mistakes. We have formulation error, and then we have data uncertainty. Okay, so we have a blunders, formulation error, and a data uncertainty. So these are different types of what I would call a modeling error. As I said, blunders are just a human mistakes. So you forgot a term, you use the wrong equation for the quadratic equation, or rather a quadratic method, or whatever you did is this just a human mistake. And this can be very, very, very problematic and really do happen in real world situations. But they are a little hard to analyze. And so you have those errors, you have formulation error, where you actually use a model that doesn't represent reality. For example, when we're trying to figure out how fast because someone pitches with a baseball or something, we may neglect a quantum well, or we may neglect an effect. And then of course, I mean, obviously that would probably be a reasonable assumption to neglect that. But I mean is something that really does come into play. But it's so small. We're going to say, oh, it's not big enough, but if we and in that case we were to neglect effects when we're trying to calculate the position using GPS, well, as we know, it's too big of error, and the solutions aren't satisfactory, and so there's a certain formulations error. Okay, so we know how the physical phenomena behaves, but we choose not to model some effects to simplify our analysis. And then of course, there's data uncertainty, where our data, the data we may took may have been unreliable. Maybe the sensor was on, but it wasn't positioned correctly, or whatever, and these things can happen too. And so these are those types of error that can occur that come into a problem. Okay, so the next type of error we have is a numerical error, and we're going to treat numerical method into different section. One is truncation error, and we'll talk about more that later. But truncation error, and whenever we talk about truncation in this book, we talk about truncating an infinite series. So this is a mathematical error that comes from a numerical approximation. Okay, so that approximations that we make coming from truncating, of course, an infinite series. And then the second major type of error that we talk about is what Chopra and Cannell call a round of error. And that is going to be different types of error that come from our numerical approximation, because we present numbers in the computer, and then we're going to talk extensively about that. I'm going to divide this into two different subtype, so that I'm going to call quantization error and error that enters in because of numerical manipulations, such as adding or subtracting a very big number, or a very small number from a very large number. And we'll talk about that a little more in sections to come, but this is a brief introductions basically to error.